Hi everyone, my name is Lauren Rhodes. I'm a research fellow here at McGill. I am not an FRB astronomer, but I'm introducing the first series of talks today. Our first talk is coming from Ashley Villar, who is at Harvard. She is joining us online. So Ashley, if you would like to share your slides.
Okay, amazing. Thank you so much. Thank you for inviting me. I'm so sorry I couldn't join in person this time, but I'll try to pop in throughout the day. Um, so I am excited to give the first talk. I am very much coming from a different world. I don't do FRB science. I don't do radio science. I typically do optical and thermalized transient science. But I think that there's obviously a lot of overlap in the key scientific questions we're trying to answer. And I want to highlight generically some of the things that we've been thinking about in supernova science in particular for a very long time now that I think FRB science is also becoming increasingly interested in. I want to start by highlighting just the incredible complexity and breadth of time domain astrophysics, and that's really the theme of this talk. Here I'm showing this ChatGPT generated image, one, to show my love of ChatGPT, but two, to show that there's so much interesting physics that can be probed from singular objects like the neutron star, that can be observed across multiple wavelengths, that can be observed across multiple timescales. That can really give us deep insight both into how these sorts of exotic objects are formed, how they spend their life both early on and then as they fade away, and then how they kind of populate and change the cosmos around them. And so I think that what's really fun about this is that it's so multifaceted to study this phenomena in our night sky that are really changing on very human timescales. What I want to emphasize again is that the diversity that's being driven by these events fundamentally, at least to me, largely come from two key ingredients. One is understanding the progenitor systems themselves. So are these things coming, are the bumps in the night that we're looking at currently coming from neutron star systems or white dwarf systems? And what's actually powering the transient observation that we see? Is that coming from radioactive decay for me, from my optical world? Is that coming from some sort of magnetic field effect? Answering both of those questions in tandem is fundamental to really mapping out this full picture, which is largely what we're after. So that's going to be the broad roadmap of what we'll talk about here today, is loosely trying to piece those sorts of puzzles pieces together. But I also want to take a human view really quick and just emphasize to what I know everyone in the room already knows, what a cool time it is to be in time domain astrophysics. So much fun. So here I'm showing a version. Oh, did it get cut off? It did. So on the x-axis, that's the years. And then on the y-axis is the cumulative discovery for three different, I don't know, kind of characteristic classes of transients, probing the gamma rays, optical, and radio. So I'm showing you supernovae. I've rescaled it so that they all look a little bit closer to the same, which has been experiencing an exponential growth for the last few decades just due to technological advances in CCD detector technology, still CCDs. Gamma ray bursts, which have been experiencing linear growth for quite a while. I hope that they get their own explosion, but it's challenging to find these space-based probes. And then really exciting, of course, in blue is FRB growth, which has just had this absolute explosion of discoveries thanks to dedicated missions like CHIME, DSA 100, that are fundamentally changing the field itself. And I'm out of date. So this is coming from just an online FRB catalog, but I know that there are thousands at this point FRBs discovered. Looking forward, so just in order 5 years, I think what's really fun is that most of these fields are going to continue with this explosion in exponential or even past exponential growth. For supernova science, we're incredibly excited right now about the Vera Rubin Observatory that just took its first images recently. That will change our discovery rate from order 10,000 events per year to 1 million events per year. FRBs too, my understanding is that with, again, increasingly large online missions here, like DSA 2000 is what I'm most familiar with, we should be expecting also orders 10,000s, if not 10,000 events discovered annually, which is really exciting to think about. If we have those localizations, we can really piece together the progenitors and the launching physics of these sorts of phenomena. A little sad tale is GRBs, again, they won't quite have that explosion. They'll probably continue on their linear growth. I hope they continue at least linearly. We'll see. Okay. So this is all just to say, like, super fun time. We are all, I think, entering this exciting big data era together, although of course that means different, let's see, what do I want to say? Different sorts of data volumes that we're experiencing and different time scales. So back to science, though. What can we do with this influx? I think one of the most exciting things that's also just very simple is that we can map out diversity. We can really start to take these huge populations, capture some easy features from them, and make these sorts of plots where we understand, can I actually classify the underlying physical phenomena and progenitor systems just by sorting them into these simple features. I don't know what Daniela will talk about, but like you can imagine doing this in much more complicated ways to really help us understand the underlying physics. But this is a very common sort of plot where I just measure some form of a duration, how long that event lasts. And here we think about exactly where I'm observing it and how long kind of coherent bursts last, versus how much energy is that thing outputting, so some form of a luminosity. Why these are so rich, you can see right away. You can see that there are often gaps that are not due to observational effects between clear classes. Here, just highlighting things like true FRBs versus more typical pulsar radio, repeating radio behavior. We can use this then to make broader physical statements, even though these are pretty simple to measure. So if I take the same kind of picture and zoom out, this gets much more complicated, I realize, but what I want to highlight is that many phenomena are emitting in radio waves, and their position here is telling us really fundamental statements about their physics. For example, we can make simple statements about whether or not the radio emission we see is coherent or incoherent. We can also understand, so saying in a different way, if we're seeing synchrotron emission, some form of thermal emission, just from understanding these simple features. This is also something that is very much done in the supernova world, where we also plot kind of these characteristic timescales and how much energy is being output as a function of time. And we similarly see these clear kind of separations that are telling us about the underlying engines themselves, tied to whatever progenitor is pushing that engine. In our world, I will say that there is a complication more on the timescale side of things, in that because I look at the optical, that's typically thermalized emission, which just means that my photons have been rattled around in the ejecta material. The localized ejecta, to be clear, this is not a line of sight effect. That kind of fluffs out it blurs out these blobs and makes them actual blobs. So I'm not looking directly at the emission mechanism. I'm looking at it pass through some sort of filter. I'm not an expert in radio. I think there are obviously, though, kind of similar effects that you see too, this blurring function that complicates the picture. One of them is, of course, understanding dispersion effects. So may or may not be localized, but that blurs out this kind of system that we see. The other one that's not really, I don't think this is true for FRBs. We also, of course, this is, oh, I don't have that. I have it here. This is secretly an isotropic equivalent energy. So we're not assuming any jetted physics or anything like that. So there's this blurring function that obviously occurs in these sorts of phase spaces, but even so, there's such a rich amount of physics to explore in mapping out that diversity. A third axis of diversity that really complicates things again is that we can observe across an incredibly wide range of wavelengths to probe different physics of the same phenomenon. And I think we know this, but let's be clear. All the way from the radio, where we can be looking at, again, coherent emission, if I'm thinking about FRBs, thinking about synchrotron emission, particularly for me, from supernovae, through the IR/optical UV, where I'm really probing thermalized emission. That's something about the photospheric phase of these events when they're optically thick. Through X-rays and gamma rays, which once again gets to synchrotron, non-thermal emission functions that probes more things like jetted emission or, again, interaction. So that's just to say the phase space that we see observationally is incredibly diverse because of these multifaceted effects. Some are coming from the physics themselves, some are coming from how we're observing the physics. Going back, now, instead of looking observationally, let's turn for a second and think of it more that we're excellent theorists, and what if we really could map out exactly the pathways of these events? This is also a very complicated picture. Here I made, sorry, it's not easy to see, but I've made this kind of flowchart diagram to just really show the complexity of the final transient events that we see. I'm mainly highlighting supernovae, what I do, and their initial progenitors, we think, which can range from, of course, compact objects to massive stars, and the flavors of how they undergo their lives. So whether that be from binary interaction, or undergoing a core collapse, and then as their compact object, continuing to undergo some sort of interaction with baryonic material around them, it causally changes the sort of transient that we see that further leads to these complications. So it's not just a observational curiosity that we see so much diversity. It really is being driven by the underlying astrophysics. FRBs are fun because I think that we don't quite know where they live yet on this already complex graph, and I hope and assume that there'll be some discussion of the many theoretical pathways we might see. Okay, let's dive in a little bit more, just some lessons learned, particularly from, I'll mainly focus on core collapse supernovae, of specifically what can we glean from observations of progenitor systems, and then we'll talk a bit about power sources. Taking a step back and just saying a statement first on some supernova science. So I mainly study core collapse supernovae, which I think are probably very relevant for FRBs. You can tell what team I live on for their progenitors. So core collapse supernovae are from massive stars that are spending their life burning away, fusing elements into heavier elements. They do so at the inner cores, the hottest and highest pressure points of their star, and they actually form these onion structures. This is a cartoon, but they really do kind of form these onion structures of unburned material from the lightest elements to the heaviest elements before fusion becomes an endothermic process. And if we assume that supernovae are from single massive stars, they're living their life, I think what's quite beautiful is that we can map out how we think those stars will eventually explode. There's this whole zoo that's taxonomy, that's quite complicated and we won't get into, but basically we take spectroscopy in the optical of supernovae, and we look to see what elements are present or not present. But more importantly, that's telling us whether or not envelopes of so the relatively low density mass are present within the star at the time of explosion. Sometimes it turns out stars are seemingly missing all of their hydrogen. That's very abnormal because we typically don't burn through all of that hydrogen. Instead, what we think is happening is if I am a large massive star and I lose mass via metal-driven lines, then I can lose sufficient mass throughout my life to be totally stripped of that material. And that typically means I have no hydrogen, and sometimes I even have no helium present. I'm just a kind of core, a carbon-oxygen core. Okay, so that's to say that with our basic theories, we can kind of map out what we think is happening here. partially why we do this. One, that explains the observations we see, but also then we can map that back into what I call the progeny, or like what the compact object that's left over after that explosion. I apologize, this picture is always like very hard to read, but this is a great review paper and one of my favorite pictures. So what I'm showing you is exactly the same sort of phase space of what is my initial ZAMS mass, what is my metallicity, but now I'm color coding it by the compact object type that I will leave. And again, assuming that I'm kind of a single massive star, I can map out if I will leave behind a neutron star, a black hole, or if actually I might even leave behind no object if it's a direct collapse. Okay, note this has gotten obviously much more complicated, even the single star picture. But that's just to say that there is a direct link, although challenging to make, between the observations we see from these supernovae all the way to what it's actually leaving behind. So that seems great. Maybe the progenitor question is quite straightforward if we just work on exactly those observations. Of course, that's not true. So one of the biggest complicating factors, in my opinion, of the diversity that we see from transients generically is the fact that massive stars, basically all massive stars, live in binaries. And many of those live in binaries that cannot be even treated as isolated stars. That means they interact with each other. This is a very extreme scenario from NASA where two neutron stars hit each other. But throughout the life, two binary stars might continuously interact. In particular, what we can imagine, if you remember from your stellar physics class, I can fill up my Roche lobe and actually accrete onto my companion star, changing both their chemical history and how they will evolve, but also changing myself and how I will explode. So in this, oh, I forgot to cite, but in this cartoon image, I'm showing here accretion that eventually leads to me stripping my hydrogen envelope without needing to be an incredibly massive star, without needing to have my own metal-driven winds. And that allows me to explode as these kind of complex subtypes of stripped stars that otherwise would be clear signals of things like black holes in a wide range of masses. And in fact, we think that common envelope physics can continue to the secondary star. It can also lose its envelope, and eventually it too can explode as a highly stripped event. So these interactions directly change the observations we see and complicate the sort of compact objects we can infer left behind. I'll also, well, we'll get to that in 1 second. In supernova science, I'll say this is kind of the holy grail question. It's like, okay, what is that mapping then? There are interesting theories that say maybe binaries can, like magnetars, can fix everything and explain everything that we see. Maybe we can connect together this complex zoo of observational signatures of having an envelope, not having an envelope, interacting with stuff I've like erupted off, seemingly having maybe engines formed. Maybe I can connect all of that with just different scenarios of a binary system in different configurations that changes the timescale at which I interact before explosion. And then there's a sense in which I've simplified the problem again. I've removed a lot, not entirely, but a lot of effects of like the mass of the progenitor star, and I've replaced it with this complex phase space of the binary system itself. I think that this is not the solution. This is to emphasize that this once again just means that the lives of these stars are incredibly complicated, and understanding where their final endpoints is not a very straightforward mapping necessarily. And as a last point, as we saw in our cute GIF, these stars are also obviously, well, occasionally, they can also hit each other and actually collide and merge. Again, I'm showing you a biased view. Here I'm showing what happens when, imagine a scenario we've already cartoonified. I have two stars. They've interacted throughout their life. They've left behind two neutron stars. If those neutron stars then collide, we see yet another thermalized transient that we can observe called the kilonova that importantly, physically highlights where the heaviest elements in our universe are being formed, which require rapid neutron capture. What I want to say, though, is that the time scales of those sorts of events, so me exploding as a massive star versus me colliding with a companion, are incredibly distinct. As a massive star, I'm only going to live my life for tens of millions of years. Really, like, snapshot, nothing. However, once I've died and left behind some compact companion, ignoring common envelope physics, one of the only ways I can lose energy in my binary is through gravitational waves, and that's very inefficient. And so actually getting to a merger system is an incredibly different pathway of a transient in terms of time scale and, of course, engines than it is from a core collapse supernova. And yet we still observe these things in the same way in the optical and the gamma rays and the radio. Okay, so all that's just to say that the zoo of observational properties of the transients that we observe is only partially driven by progenitor scenarios, which includes kind of complexity of intrinsic to stellar evolution, but also very, maybe more importantly, binary interaction and how that changes stellar outcomes. Switching gears just a little bit, I also want to highlight, though, how we don't, I think it's clear now, we don't actually observe progenitor systems. That's not what happens. In the transient, we observe some underlying engine or power source that's driving some sort of explosion or eruption, something. This is also incredibly diverse, even just in supernova science, although I'm highlighting slightly broader than that here. In a most traditional supernova, we imagine that what we learn about in class typically is that, okay, I have been fusing heavy elements. I finally have gotten to nickel. That nickel's unstable. I radioactively decay. That powers the explosion I see. Fine. It turns out, though, I think especially important for this audience, there are many other engines that can also feed back into that ejecta and that explosion and completely change the observations that we see. In particular, I want to highlight this idea of a magnetar. If I form a neutron star, that neutron star happens to be rapidly rotating, it happens to have a high magnetic field, we think that that neutron star can very quickly spin down by feeding its angular momentum into the expanding ejecta of the supernova itself. And that acts as an additional engine that drives the explosion and contributes, especially at early times, more energy than, well, and late times, than radioactive decay. Here I'm showing you a theorized light curve that has both nickel 56 contributions, that's radioactive decay, and then a magnetar injection, and just kind of arbitrarily scaled so that they look similar energies. Importantly, you can see that they have clearly different effects, though, at late times, despite having similar peaks and rise times. So even though these can both come from the explosion of a core collapse supernova, they look incredibly different. And we see this. We're pretty sure we see this. When we look at supernovae, there's an exotic class called superluminous supernovae, where we can do tests of looking at the tail, and we can ask, is this following, and here, I've chosen one that's a little ambiguous, but they're not ambiguous. We can ask, is this following the expectation of radioactive decay? Or is actually the decay following exactly what we expect for a magnetar system spinning down? And we have found many lines of evidence that do suggest, yeah, these sorts of exotic supernovae that are stripped of their hydrogen, their helium, do seem to have magnetars. Although we're still totally unsure what the origin of those actually are, meaning the progenitors themselves. I will skip this just for the sake of skipping it, and just say that this is to emphasize the point that the engines are causally linked to the progenitors themselves, but independently contribute to the diversity that we see. As a last is my last little theme, which is just to say that the context of these guys helps a lot and matters maybe as much as the explosion itself. Understanding the environments that these sorts of explosions come from is fundamental in connecting the progenitors. Maybe not the engines, but like definitely understanding the question of the progenitors themselves. Here to showing you a picture of two galaxies. One is happily forming stars and one is red and dead. And the transients that we see are a sample, one star, from this massive collection of billions of stars that we call a galaxy. It's not a random sample, but understanding that the stars within a galaxy are young, therefore massive, is very different sort of collection I can pull from than a galaxy in which the stars have had giga years, in which they're no longer forming massive progenitor systems. It can directly tell us that the progenitor of the system that we're seeing is from something young that has recently been birthed, or with some sort of delayed channel that has needed a long amount of time to actually explode. Even just zooming into core collapse supernovae, this picture, host galaxies give us a lot of clues that there is some key difference between their progenitor systems. This is a really confusing plot. I just want to show you two subsets. There's this one and then this one. Superluminous supernovae are the one that I'm highlighting that we think come from magnetars. Really interestingly, they love very low mass, which means very low metallicity and also high specific star formation rate, galaxies. Really weird. There's something about maybe that they love massive progenitor stars, maybe something to do with binarity, but they love to be preferentially in these weird galaxies. I want to contrast that with type 2s. Sorry, the naming scheme is so annoying. They're like the standard, if you hear core collapse, that's what we're talking about. They typically follow what you think, just like massive star-forming galaxies. If I'm forming galaxies, I preferentially blow up there. Very different sort of populations here. These love, the normal type 2s love high metallicity galaxies because those are bigger. Whereas superluminous, the magnetar ones, really have a distinct preference. This is weird when you fold in this idea of FRBs. I'm not the expert on this. This is a massively, very quickly growing literature. I'm just highlighting a few examples. And again, apologies, it's complicated. I'm showing you here the distribution of galaxy masses, cumulative distribution for FRBs in black, and then comparing it, and I was not on this paper, but comparing it to other populations of transients. And particularly, the takeaway of this paper, the claim of the authors, is that this seems consistent with core collapse supernovae. Seems like they prefer to trace ongoing star formation, massive galaxies, high metallicity, just like the type 2s, which I will note do not make magnetars. Okay, more recent work, although I don't think this has been reviewed yet, I don't know, has shown, again, through kind of statistical analysis, you can basically just ask, unfortunately, metallicity and star formation are correlated because mass is, I have more stars, I have more star formation. So you can ask a question like, what's actually the causal driving factor? Is it mass or is it star formation? That's what these authors do, and they basically claim that actually it seems like these are more mass weighted than FRB progenitors are more mass weighted in preference than they are star forming. More like type 1As, which is a very delayed channel. A little confusing since most of them seem to be coming from star forming galaxies. The incredibly precise localizations are helping unravel this story a bit more, although it's still very complicated. And I just want to highlight this recent result from CHIME, where a very high precision localization allowed it to be associated with a FRB associated with like a clearly dead galaxy. Clearly, this FRB at least seems to be coming from a delayed channel. But to highlight, that's not actually true for most FRBs. Once again, very recently, I'm highlighting a CHIME result. A very high precision localization has allowed it to be associated to a very nearby, although not exactly on, H1 region. That again highlights, in this case, that it might be coming from a younger sort of population. I think that increasingly these localizations are key, and the host galaxies are a very, very helpful diagnostic of the progenitors themselves. Okay, in my 0 minutes, I'm just highlighting here, again, emphasizing what a fun time to be in time domain. I haven't added all the FRB missions because I know that you have a whole session on it. But at least in the optical UV, incredible amount of new mission coming up. Well, hopefully. that should be continuously changing the way that we're viewing these events, both in kind of the wavelength space, but also just the rates at which we see them. So I'm going to stop there, and I'm happy if I have time to take any questions.
Thank you, Ashley. That was an excellent start to the conference, I think. Not that I'm biased at all. I also work on other types of transients. So now we have a couple minutes to invite questions. So do we have any questions in person or online? And please don't be shy. Seriously? No one? Oh, Jason. Okay. I don't want to throw this. Yeah, no, I have zero hand-eye coordination.
Yeah, thanks for the nice talk. So you distinguished supernovae that make magnetars and don't make magnetars. But to be a bit more specific, I think you mean the ones where there's obviously a role of the magnetar at early times in powering the explosion, right? I guess we're still kind of vague on which supernovae produce magnetars that are maybe less rapidly spinning, but still become magnetically powered, right?
Yeah, you're exactly correct. So the superluminous ones are ones that at early times contribute sufficient energy, presumably from spin down, that they impact the thermal transient. But you are totally right. We don't understand what do I want to say, the connection between that much smaller time scale effect and longer time scale. And to emphasize, the type 2, so the typical core collapse, of course, can lead to neutron stars, as we saw in the pictures I've shown. But there seems to be a preference for incredibly strong magnetars in these dwarf galaxies, so low metallicity environments.
Awesome. Any other? We have a question online. Oh, we need to. You need the thing, the cash box. Oh my god.
Hi, hello. Can you hear me?
Oh yes.
Beautiful. Thank you. Hey, thank you, Ashley, for the great talk. Forgive me if you had mentioned this earlier, but in terms of potentially identifying in the future FRBs that actually are originating from core collapse supernovae, what do you consider to be, like, would the smoking gun piece of observational evidence be detections of afterglows or afterglows at certain times after the occurrence of the FRB? What do you consider to be things that would be useful for us to actually yield that kind of an association?
Yeah, so I will slightly not punt it, but you're not in the room. Tara Nayeftakari, I think, has very interesting work, and Brian Metzger on the theory side. And I want to make sure I say it properly. I think I will. So one thing that we might expect is that if we have, Tara, you should correct me though if I'm wrong, a pulsar wind nebula at much later, like order decade after the supernova, we might expect then FRB sources to emit from those exact same objects. And so one observational, let's see, what do I want to say? One observational campaign you can imagine is to look at these sorts of known supernova, but nearby sources order years to decades after their explosion themselves. This has not yielded a notable smoking gun signature yet.